Hi guys, and welcome to the lecture series for the course of Applied Transport Modeling with Visum. Today we will have our lecture 8th on trip generation. My name is Mohit Qureshi. So looking at the schedule again, it's our eighth lecture today, and last week we had a lecture on trip generation. So basically what we're trying to cover is the four-step modeling technique on Visum, which includes trip generation, distribution, mode choice, and traffic assignment. In the previous lecture, we were basically started with our network containing the special zones and the supply side of the network, the roads and public transport, and along with we had our zonal attributes and household travel survey data. And from the household travel survey data, we basically tried to create different demand groups and finish up getting trip generation and attractions for all the zones. And in this lecture, basically what we'll have three different types or three different major parts. The first part will be that we will try to estimate the gravity model parameters for trip distribution. The idea is that basically to convert the trip productions and attractions from which are the output of the trip generation step, and convert them into an OD matrix which has trips, zone to zone trips. So if you have in our case study, so we have 24 zones, and in the trip generation we got the productions and attractions for these all 24 zones for a given demand group, like home-based work. And in this step of trip distribution, we'll basically start from this trip production and attractions and convert this into an OD matrix, which will have a matrix of 24 by 24, having in its cells all the trips from each zone towards all the other zones. And to have this, basically there are three major components that we need to work on. The first one is estimate gravity model parameters. So basically we'll work on to convert this projection and attractions to an OD matrix, or by the step of trip distribution. We will use the gravity model technique, which requires an impedance matrix in Visum and observed trip length frequency distribution, which will extract from the trip survey using R, and then the procedure sequence which will for calibrate function in Visum. So basically in this procedure sequence we will try and calibrate our gravity model parameters using the TLFT distribution from R and the impedance matrix. Once we have the gravity model parameters, we'll basically then use the procedure sequence to perform the step of trip distribution, giving it in the input as the impedance matrix plus the model parameters, the gravity model parameters. And once so the output of this trip distribution will be basically an OD matrix. And also the third step that we'll also do is try to evaluate the results that we have. So this result would be basically a comparison between the observed TLFD that we got from the trip survey versus the modeled TLFD. So when we are modeling when we convert this into an OD matrix, we also have a TLFD that is will be like from the model. So how we'll get into details for this, and also we will extract a coincidence ratio between the model and the observed TLFDs to understand how well we were able to replicate the behavior from the trip survey to the model. So in the previous lecture, we'll have a basic recap from the previous lecture. In the previous lecture, we were working on trip generation, and what we started with was to try and define the demand groups. If you remember, we had a number of different demand groups to, like, basically we had like two different types of demand groups. First of all, one is based on the trip purpose, so like home-based work, others or non-home-based trips, right? So this is one type of demand classification where you try to create demand groups based on activity. The other one was based on person demographics. So we saw that we can have car or no car, we can have income based, we can have male or female, we can have yeah, car ownership and things like, and age groups as well. So these are like creating demand growth based on person demographic attributes. Yeah. So next, okay, then what we first created the demand groups that we wanted to work on, and then we just read the data in R. And also once we read the data in R, we wanted to extract the production and attraction rates using cross qualification and linear regression techniques. And once we had the rates for production and attractions, we went to Visum. We set up the same demand model that we assumed, or we classified in the start, and we said we replicated the same demand model in Visum. And then we added the zone attributes that we had from survey data, or not from survey data but from the Excel sheet. We copied the same zonal attributes in our model, and then we created a procedure sequence that for trip generation step. And in this procedure sequence, we specified the attributes that were like the production and traction functions, and also the metrics balancing. So I hope you remember the concept of metric balancing for home based and non-home based. So we say that the for home based we use the production totals, and for non-home based we use the attraction totals, because home based are always based on population. So we can say that the production total is more certain because we are more certain about the population than the other things. Yeah. So and then the lastly, what we did was like we executed the procedure, and we also had some results visualization, how we can see the productions and attractions in the zone list table. Next, so today, whatever the purpose of, so we're going to discuss trip distribution. And the basic purpose of trip distribution is basically to convert zone production and attractions to an OD matrix that is from origins and destinations. So origins and destinations are zone, and so for each zone, its origin towards all the destinations. So what are the number of trips for each zone towards all the other zones? Yeah. Trip generation basically focuses on generation and attraction of trips from each zone, irrespective of the direction of travel. Trip distribution focuses on creating origin destination trip pairs by connecting productions and attractions from each zone. Yeah. So there are a number of methods that can be used to basically convert the production and attractions into an OD matrix. Uh, Basic, we can still, there are three major types of methods we can state here. So the first one would be growth model. Like, so a growth model is something that, okay, it's similar to what we had in as expansion factors, if you remember. So basically we did a survey which where we had a number of trips recorded from different households and different persons. Yeah. So if you have enough, significantly enough sample, observed sample, and you have the population attributes, so basically you can scale up that the attributes that you received from the sample, or the results that you received from the sample, you can scale this up to the whole population. Yeah. That's what we were doing with the expansion factors. Now is the same if you can if so this is the same way. The growth model would be something like, okay, if you try to do an origin destination matrix survey. So basically, an origin destination matrix survey would be like, okay, if you try to cover the overall network and try to see that, okay, try to create 5% or 10% sample of the vehicles, and trying to stop the vehicle and taking the roadside interviews, asking, okay, what are your origin, what is your destination with the trip purpose. So basically, this will give you already an OD matrix information on a smaller scale for a sample of 5%, let's say. And then using this same information, considering that you know the population of all the zones and and also the other attributes, you can basically try and scale up the origin and destination matrix that you see from the sample to the whole population. The next approach that is used in doing the trip distribution step is the gravity model. And this in this approach, basically what you do is like, it's similar, that it's a concept that is borrowed from physics. So you know what is gravity overall, right? So what is the basic idea of gravity? Gravity is basically that two large masses attract each other, and this attraction is that it's a multiplication of the mass that these two bodies have divided by the squared distance. Yeah. So similarly, in this trip distribution version, what we do is like, larger zones with bigger populations will attract more trips within each other than the smaller zones, and also the distance apart. So if the impedance to travel from one zone to the other is large as well, although they have bigger masses or bigger population that can create more production and attraction, they will might have still lesser distance. So the distance between them is an inversely proportional to the total trips, but the size of the zones will be directly proportional to the total trips. Yeah. The last type of them is destination choice model, and this is basically a discrete choice model technique where basically you try to use your logic models, and you are basically calculating utilities for all the zones for all the zones as destinations. So you try to create utilities for all the zones. How the attraction utilities, you can say that, okay, if it's a city center, it might have more attraction utilities because of a lot of things. It's a more mixed zone, a lot of shopping and stuff, leisure and all. So basically for each zone as a destination, you try to find its utility to attract the trips, right? So this gives you also the information like to distribute the trips from all the produced to distribute the productions from all the zones to different zones. Yeah. So if you have one zone which can produce 1000 trips, now where are they being attracted? That is an important question, right? So this attraction will be based on a utility function of how all the zones can actually attract trips from another zone. Yeah. Normally, as it's mentioned here as well in the note, that okay, normally gravity models are the one that is mostly being used. And let's see what is basically a gravity model. A gravity model, as I told, is about from the physics with a concept like mass gravity. Larger zones will have more trip attractions than smaller ones. Yeah, zones that are closer to each other will have more trip attraction than the zones that are further apart. So distance is basically inverse proportional, and the mass or the population of the zone is directly proportional. Okay, the second thing is an impedance function. Now, this is basically a concept that says that okay, what is the because similar in the gravity model, like in a normal gravity concept, two masses would have a distance in between them, right? This is a direct distance in terms of physics, but in terms of traveling in travel modeling, this is not a straight distance. This has to be what is the impedance or what is the resistance between traveling between two zones. Yeah, and this has been calculated using a impedance function. Now what is an impedance function? Impedance function is described as a cost to travel between two zones. It's rather simple, right? So there can be different attributes that affect the impedance function, and we need to use them to basically calculate what is the resistance between traveling two zones. Yeah. So the most probable elements that we consider are travel times. So if it's congested, you have longer travel time. If it's less congested, you have shorter travel time. Maybe off peak, you're more likely to go to city center than a peak hour because you don't want to go there. It's a lot more congested. It will take more time and you will be stuck there and all. It will be rushy as well. So travel time is one thing. Second is distance. Distance is rather simple. Then travel cost, that is also very important. That okay, if you want to go to a city center, you might need to give a lot of parkings. If you want to use a motorway, you might need to give tolls, and also like it's more additional because of these than just the distance. I mean, the petrol cost and all is rather a function of the distance or the travel times. Yeah. And then okay, tolls for car, number of transfers, transit. This is also very important. This is a very major impedance um, type for public transport, because like considering just a one transfer, then no transfer can be really like as the transfers increases, the impedance is really getting higher for a public transport to be used as a mode. Yeah. So basically, to find an impedance between two zones, we'll always try to use a combination of several elements to evaluate the impedance given as a function you can see under. Yeah. So we will have different coefficients for all the different types of elements, and each of them would have a certain effect on the impedance. Yeah. And this is I mean I don't want to go away from the topic a lot, but this is something also similar to, you can say, the utility function or passenger or person preferences, right? So it's really rather important here that okay, we should also understand that why do you want to work on demand groups. If you consider that you want to create demand groups like income based or age based, if you consider first the income based, like if you have a demand group that is high, low, or medium income, people would have which have low income would rather have a larger A3 or the coefficient for cost, because I mean they might say that I can travel more, but I would like to pay less. Versus someone who's rich would not like to spend a lot of time traveling, slower traveling, I would say. Maybe he wants to spend the same amount of time to travel, but like he doesn't want to get stuck in congestion, or would like to have a lot of transfers because he's already rich. So for him, cost is not rather that important than a low income person. Now, so impedance between different demand groups can be very different, yeah. So that's why sometimes when of course it depends on the purpose why you're modeling. So if you have a certain if you need really to create a model which is actually trying to differentiate between income based groups or age based groups. Age is another factor, like younger people might would like to travel more than older people, yeah. So this is also like something that is like comes here where you like affects a lot here, that okay, different demand groups, why do you want to create the different demand groups, yeah. And also like this impedance function is something similar to what we say also the utility functions. I hope you understand the idea for impedance functions now. Yeah. So next, we will also consider that okay, there have been a number. So we already considered U. We can call it similar to a utility you want to travel, or it's not directly a utility, but it's similar to the idea of utility. But this is basically resistance. Utility is something that you want to do it, right? You want to travel. What is the utility if you want to travel? But this is opposite of that. That is the resistance why you don't want to travel. The travel time is more, I don't want to travel. The cost is more, I don't want to travel, yeah. So now the effect of this resistance, how does it affect directly the travel? Now this is being used. So this is basically the impedance, how you evaluate the impedance. Now there have been a multiple impedance functions that have been proposed to be used in the gravity model, yeah. So here there are like five different impedance functions stated, and they are basically what we are trying to use here is like different types of equations with either one, two, or three function parameters. So what we try to do basically is we try to use one of these, and once we get the impedance, how people are actually traveling between zones from the trip survey, we try to calibrate or try to find the values for these functions. So let's suppose we used to try to use logit model, and we already know what is U. What we don't know is basically what is C. Now, to understand or to evaluate C, what you will do, you will probably try and go and see how people actually traveled. And this is the idea of this lecture. So we'll go and see, okay, how are actually people traveling in our trip survey. And once we get the idea from the trip survey, we'll use the information from the trip survey to get a value or calibrate a value of this C. And this is the whole idea also, that once you get the value of C and you do the trip distribution, and once you do the trip distribution, you get an OD matrix. And then what we will do, we'll try to model a TLFD. I will give you the concept. But the value of C we are calibrating is exactly the error that we will have. So we will try to calibrate from the observed trips these parameters, and we will use these parameters in the model. And once we get the model output, we'll compare this model output with the observed, and we will get an error that okay, 95% is represented or 96%. And so this error is actually when we are trying to calibrate this impedance function. So to start with, basically, what we'll do, like, okay, so as I told you, we need to extract a few impedance elements to find the impedance between different zones. To simplify things, in this lecture, we'll just use a simple impedance function for car, let's suppose. So what we'll do is like so to get an impedance in Visum, we will go to the procedure sequence and we'll create a new procedure. And if you see, there is like also a tab here that is matrices. So normally we are going demand model and the four steps are there, but here we will basically do, we'll go inside matrices, and inside matrices we will create, okay, calculate PRT skim matrix. So skim matrices are the matrices that try to find the attributes between different zones, yeah. So we'll select calculate private transport skim matrices, and then in this we use the reference object as car. So right now we want to use private transport, and we say that car Okay, bike and car are the private transport modes we will say want to use for the car. Yeah, so we'll go for car, and then in the next variant file, so we'll use the different attributes that we want to extract in this scheme matrix. Yeah, now basically this is an impedance that we want to calculate. It can be distance, it can be travel time, it can be cost if you have in the model. So what we are trying to do here is basically we want to find the trip distance, and so basically we'll just simply check the box to calculate trip distance. But also another important thing is, okay, path search criteria. What is the path search criteria? Now this path search criteria is important to say that, okay, this is something okay, what is the shortest path between the zones? Yeah, so how do you find the shortest path? There can be multiple ways to go from one zone to the other. So what is the shortest path that really you want to use to find the path between different zones? Yeah, so here we use t0, that means free flow travel time. So we want to find the path based on free flow travel times. So when you will basically try and run this procedure sequence, setting up the trip distance as the skim attribute, and then okay, search path as the free flow travel time, you will basically get a matrix that gives you zone to zone distance. Yeah, so if you see this matrix, you have 24 rows, 24 columns, and each cell is basically from a zone to a zone. What is the distance? And it's, of course, it's a symmetrical matrix that, okay, this the corner, the values that are above the diagonal is also the same as the values below, almost. I mean, somewhere maybe you have one-way roads or something like that, there you will have a different value, but mostly you will have similar values. Yeah, so now you have a distance impedance matrix for car between the zones. Now the next thing you want to do is you want to extract this. So okay, so one other thing that we want to do is like, okay, we want to change the diagonal of the matrix from 0 to a non-zero value. And so because I mean, if you don't have a value here, it will be like, okay, there is no impedance, and most of like it's free to travel within the zone, which is not true. So what we'll try to do, we want to set some value that is non-zero for within zone trips. Yeah, and to do that, we say that, okay, we normally right now we're just putting that 0.5 kilometer as the impedance, but it should be basically one idea would be, it should be basically the the average size of all zones. Yeah, so let's suppose the diameter of all the zones, I mean some mean value that defines, okay, some zones are larger, some are smaller, so based on their size, trying to find a mean value of a radius or a diameter of crossing the zone would be a nice value to use here. Yeah, so now what we'll do is like, we will try to extract this impedance distance matrix and try to use it in R. So to extract this, what we'll do is like, we will go to OD pair, right click on OD pair, then list, and then open the OD pairs list. And here basically what you see is like simply from zone to zone, what is the matrix values. Yeah, so these are like OD pair table. So from zone to zone, from zone to zone means origin and destination, and OD pair, origin destination pair. Yeah, and it has a value that is from the scheme matrix. So here you can see like for all the zones, what are the values from those scheme matrices. And here what we'll do is like, we will try to export this into an Access database. So selecting this yellow icon from the bar, and then clicking on it, and then just trying to export as MS Access 2003 or earlier, and pressing OK. Yeah. So once you'll do that, you can basically go, you will have to also specify the file path or something. So basically you can just specify a file path and save it somewhere in the folder directory that you are currently having all the other course material. So once you save it, what you'll need to do next is try to go and open a new Excel sheet. And once you open a new Excel sheet, I'm going to show you all these things on the hands-on once we finish some like let's say once we finish the impedance. Yeah, just till here. So I'll go back to Wisdom. I'll show you the way I showed in the last lecture. So basically the idea would be, try to open an empty Excel sheet and load, go to data, and load the database as a table. Yeah, so we do data, get data from database and from access database, and you can see the OD pair as a table, and you can simply press load. So let's go to Visum file and try to do the same thing as as I'm discussing. So I would have to start from here. So starting in our Visum model, where we left from the trip generation lecture. So basically, in our procedure sequence, we had completed the trip generation procedure. And next, what we want to do is basically try to create the impedance matrices as we saw in our lectures. So first, we will basically create another procedure sequence. And inside this, we will go to matrices and create a private transpose scheme matrix. Press OK. Then we'll define the reference object as okay for which we want to create the impedance matrix. So we'll select car as our mode of transport, and then in the variant file we basically select what are the attributes you want to find in the scheme matrix. So basically you can find directly the trip distance, the free flow travel time, toll, and other different impedances. So user defined impedances as well. So for now, as we said, we will try and calculate the trip distance um, as an impedance. And to do this, we'll also use like to search the paths, the shortest paths between the zones. We'll use this path search criteria as the free flow travel times. And to do this, we'll just select T0 and trip distance and press OK. And next, we will basically simply run this procedure sequence. So we'll unactive the trip generation one and just activate this one and run this. And once we are finished here, we can basically go and check if the impedance matrix is created. To do that, we can have there are two tabs here on the left side of Wisdom. So one is for the networks and the other one is for the matrices. If we go matrices, we already see there's a scheme matrix available, then zone matrices, and inside this we have data matrix and the distance matrix. So if we open up this matrix, we see the matrix as we saw in the lecture, which shows all the distance impedance between all the different zones. So it's like the size is the same as an OD matrix, 24 zones or 24 rows, 24 columns for 24 zones, and it's the distance between each zone to each zone. Yeah. And now the next thing that we wanted to do is like we wanted to add some coefficient in the diagonal of the matrix. Yeah, and to do that we need to basically select this, so set diagonal. And right now we're defining just a coefficient, but you can define other things as well. So you can try to, as I said before, you can try to create some values based on the size of the zones as well. Yeah, so once we finish this, so this is basically a distance based impedance matrix between the zones. And next, to export this impedance matrix, we will go to OD pairs list, OD pairs. So because this is an OD attribute, so zone pair based attributes. So if we open OD pair list, we will see this attribute. So the name of this is like matrix value one. So this is the matrix here. So matrix value one, that is distance. We have this as a column between from zone to zone and the distance impedance between this OD pair. Yeah, and to export this, we'll do the access. So save list to database, and we'll use MS Access 2003 or earlier. We'll press OK, and we need to define. So I already have some other ones being defined here before. So I'll try to use the distance, the same one that I had before. So I've already exported this already. Yeah. So I'll press save just to override this. And yeah, so so this table is basically saved as a database that is like called distance, this one, so distance.mdp. Yeah, so the next thing we want to do is we want to open a new Excel file. And inside here we'll go to start a new Excel file, data, get data from database and from database access. Yeah, and here we will give the same path where we have saved our database. And So here we'll you open up simply the file that we saved our distance matrix. And this is going to take some time to load. And then out of this, we have a few types of views, out of which we want to choose basically the OD pair matrix. Yeah. So there are a number of views that you can see, and if you choose the OD pair, you will basically see the same table that we just saw in the OD pair list. And we can simply load this table and then save this table as distance dot excel file. So it's a distance excel file. Yeah. I simply replace the file because I already, as I told, I already when I was creating the lecture, I already had these files. So now this is, so basically what we have already is now is a Excel file that has all the impedance, the distance impedance between all the zones. Yeah. Now let's get back to the lecture. Here, yeah. So till here we have finished. So I hope you understand everything, how we export the impedance, how we create the impedance, what is the idea of having an impedance, and how you create the impedance matrix in Visum, and then we export it and save it as an Excel file. The next step that we want to do is to create an observed TLFD. TLFD is basically trip length frequency distribution. Now, this is a distribution that defines the trip lengths. So it's basically a distribution that shows that, okay, it's a simple distribution of trip lengths for all the trips. It's simple in simple words, yeah. So to define, so basically what we'll do is like we will try to work on the existing travel survey data, so the trips data, and we'll try to create the distribution of people doing the trips, like the people doing the people trips based on distances. So we'll basically plot a histogram of the length trip lengths for all the trips that we have in our trip table or in the trip survey table. Yeah. To start with, how we will do this is that we will go again to the R file. So to create a trip length frequency distribution in R, what we'll do, we'll start with reading the distance file, the distance Excel file that we just exported from the impedance matrix, creating the using the procedure sequence of PRT skim matrix. We have the Excel file that has all the distances between all the zone pairs. Yeah. So what first we'll do, we'll load this Excel file calling the table as distance by car. And next, what we want to do is like we want to associate all the distances. So basically what we have is like we have all the zone to zone distances. Yeah. And we have also, if you remember, we had a work trips table that we filtered from so after loading the distances, we will basically try to associate all the distances with the trip table, the work trips table. So if you remember, the work trip tables were basically what we extracted using the filter of from origin, like the purpose of yeah. So from origin home to work. So that was the idea of filtering the work trips. So once we filtered all the work trips, we had a work trip table that we used to do the production rates. Yeah, so this is the same work table that we have, and then what we'll do, we'll try to left join or associate based on which, from which zone to which zone, we try to associate the distance of that trip. So if you see basically in this line, what we are doing is like we left join in the work trips table the distance by car that we extracted from the Excel file by the zone origin and those zone destinations. So zone origin and zone destination will be like the integers of the zone IDs. Yeah. So we'll see that in R. And once we have this, so basically now we have the work trips table which have the home-based work trip along with the trip distance that they commuted to get from home to work. Yeah. Now the next thing that we want to do is to create a distribution of what is the basic trip length. So a trip length frequency distribution, which will be basically how many people are doing this home-based work trip within this within like 0 to 1 kilometer, then 1 to 2 kilometer, 2 to 3 kilometer. Yeah. So here what we'll do, we'll first create the intervals. So we are right now, so to create this histogram distribution, we'll create intervals. And so here we are creating the intervals. If you see these blue integers, not integers, but the blue numbers, that is like 1.2, 2.4, 3.6, 4. So these are basically kilometers. So the first interval would be like from 0 to 1.2, the next one will be 1.2 to 2.4, then 3.6 till 7.2. Yeah. And what we'll do is like basically we will find all the number of trips that are present that were done within 0 to 1.2, and then similarly between 1.2 to 2.4. Yeah. And to create this histogram, we are also using again the piping function. If you remember, this is the piping function. So the percentage greater than a sign and then the percentage. And basically we are working on this work trips updated. So first what we do, we use a function called mutate, which basically sets all of the so what we'll do is like, okay, it will first run this if else statement and use only work on only the trips which are which have the distance less than 1 by 2, and then we will group by say like all the distances that are less than 1 by 2, and then 2.4 that are between 1.2 to 2.4, and then 2.4 to 3.6. Yeah. So first what we are doing is using the function of mutate, we are basically setting all of them separately, all of these which are within these intervals, all the records, and then we basically group by them, each one of them. So we have 1 2 3, so we have 6 intervals, right? So we group by all of these 6 intervals separately, and then we basically summarize is the same. So we summarize all the trips which are within this group. So these two are similar that we had in the previous R code as well. So we first group by all of these interval records, and then we summarize the trip expansion factor, not the records. We don't count the records, but we sum the trip expansion factors. I hope you remember this. Yeah. And once you do this, you basically mutate. So mutate is basically a function to create a new table. So now we mutate a new table which has the records as columns as share is equal to total observed trips divided by, so share would be equal to total observed trips divided by sum of yeah, so it's a so we have to understand. So basically we are dividing total observed trips divided by the sum of total. So this means basically total observed trips within each interval divided by the sum of all the total observed trips. Yeah. So basically if we go and try to see, this is a very important and difficult step to understand. So we'll go and try to see this in R. So let's go to the R code. And so basically just this is the same code that we had from the trip generation, and we'll start again with loading the libraries and loading the household travel survey Excel file. I have the code for trip generation production as the trip production and attraction as well. So I'll just load that as it is. So we had the R code till here. And for the next thing, for trip distribution, first what we do is like we load the distance by car. And one important thing that I forgot to tell you was basically that so there's an error because I have opened my Excel file already. So one important thing that I wanted to tell you was like, okay, I changed the column from mat value 1 to distance. So this is because I'm calling the table this column by this name. So that's why I changed this. If you want to change it in the code, it's your choice. But I changed the name of the column as distance. Yeah. And then I saved and closed it. And now, to start with the trip distribution step, I am first loading this distance, calling it distance by car. So you can see this Excel file here. So from zone to zone and all the distances. And then next, we will basically associate. So this is the work trips table that you remember, right? So this is all the trips filtered which have purpose of origin home and purpose of destination work. Yeah. And now it doesn't have, so if you see its last column is trip expansion factor, and now what we'll do, we will create another table that is work trips updated by joining on the left side of this work trips table this distance by car. So based on the origin and the destination. So the zone origin and zone destination. Now, if you see this, this is the zone origin and this is the zone destination. So in here, so for the first record, it will find the distance for zone 2 to zone 4 and associate and write it on the left side as a new column. Yeah. So once you do this, you will get a new table. If you have a look at this, so you have a new table that has also a distance column, which is the distance between zone origin 2 to zone destination 4. This is 1.926, and this is the same distance that you have in distance by car. So 2 4, if you have a look, 2 4 is the same. Yeah, so this is the basic idea. So what we did, so we created a scheme matrix in Visum. There was all the distances between the zones. We loaded it in, we saved it into an Excel file, and then we loaded into our R file. We had work trips. So basically right now we are working with home-based work, right? So to this home-based work, we have already filtered all the records that were trips from home to work. And now what we added, we also added the distances on the in this table. Yeah, you understand this thing. Next, I also have this two extra code to show you the TLFD plot, the histogram plot. And if we just run this, you will see on this bottom right corner, this is the basic distribution that I'm talking about. So what we did is, like, we are basically creating intervals based on 1.2 kilometers. So the first is 0, and then the first bar is basically for the interval from 0 to 1.2, then 1.2 to 2.4 till 7.2. Yeah, and this is also the number of trips within for the given trip length. So the number of trips for between 0 to 1.2 is around almost 1000, and the next one is like almost, I don't know, something like 17 or 1800. Yeah, so this is what we are trying to create. This is the observed TLFD. Yeah, now we want to create a table summary. This is easier to plot as a histogram. So we used ggplot, and we had this data, and we said that okay, the axis x is distance and axis y is trip expansion factor, and we just created a histogram, which is relatively easier. Now, what we'll do is, like as we saw in the slides, we'll create a TLFD table. That is okay, a table that shows that okay, what are the actual values between 0 to 1.2, 1.2 to 2.4. Yeah. So to start with, what it so I mean, if I need to run this, I'll just run it once and it will all run. And the TLFD table that should be is which we should get as an output is this, which has the upper limit of the interval. So 0 to 1.2 has 792 trips, and this share, it means that okay, 792 divided by all the observed trips, the sum of all the observed trips. So 17.8% of the trips have the trip length between 0 to 1.2. Yeah, and now just to give you a brief understanding of the code as well. So what we are trying to do is, like, we have this work trips updated. What we are doing is, like, from this work trip updated, we first create, so mutate is basically to create a new column. That so in the TLFD table, we first create a new column that is called upper limit. So as you can see in here, this is the upper limit, and in this we say that okay, it will contain so it's a column which has a condition for distance is less than 2, and the column title is 1.2. So this is what is the idea. So basically we have a condition for each row, that is distance is less than 1.2, 2.4, 3.6, 4.8. Yeah, and the next thing is we create the labels. There is 1.2, 2.4. Yeah, and then we basically group by the upper limit. So we group by the trips based on these conditions. Yeah, so based on the upper limit conditions. So we have the group of tables, the group of trips that are between first interval, second interval till the sixth interval, and then we take the summary. We'll take the sum of the trip expansion, that is like the trips for the population. So if you use just the trips counts, just counting the trips, it will be the surveyed trips. But if you use the expansion factors, you're basically doing it for the whole population of the study area. So we will sum all the trip expansion factors. We'll take a sum based on all the groups, all the 6 groups of the interval, and this will be basically total observed trips. So let's see here. So total observed trips. Yeah. So the next column that we created is total observed trips, which is the sum of trip expansion factors. Now each sum is basically for each group that we just grouped here based on the upper limit. Now the last one is also we mutate, or we also create a new column which basically has the name as share, and the share is total observed trips by the sum of the whole column. So share is basically total observed trips value divided by the sum of the whole column of total observed trips. Yeah. So I hope you understand now how the code is written, how the code is working. And this is the basic idea, how we can create a TLFD table. Yeah. So yeah, let's go back to our slides. And so yeah, so this is the basic idea how you can create an observed TLFT table in R using so first you so just to recap, first we went to the model, we created a scheme matrix that had the impedance by distance, and once we had the distance matrix, we exported that into Excel file and loaded into R, and we associated these distances with our work trips. So we had the from zone to zone in our work trips, and we associated their distances for their trips. And once we had that, we basically plotted or created a distribution of our work trips based on the records. Yeah. So we had and this is what we call as like the trip length frequency distribution. And now once we have the TLFD, so okay, so this slide I should have showed you before, but okay. So TLFD is a distribution, so that will represent in a table. So we create a set of intervals with an upper limit value for each interval, and we group the elements, and lastly we find the percentages of trips for each corresponding interval. So this I already described you in the R file, in the R code as well, right? So mutate function is to add new variables. So first we use mutate to create the upper limits of our distribution interval with the element name as a character. So like here, and then we mutate to create a new column named as share with its evaluation function in front. Yeah. So we use mutate twice. So here and here, and we create another column that is for total observed trips here. Yeah. So this is also the slides that would show that okay how this is done in R. Distance by car, then okay distance here as well. We attach the distance in the work trips, calling a new table, creating a new table that is work trips updated, and then we do the piping 3-4 set of lines to create this TLFD table. And also we can get a histogram that I just showed you using ggplots, and we create a geometric histogram showing what are actually the shares or the actual trips. So here we are actually plotting the number of trips for each interval. Now this was the prerequisite that we required to to basically calibrate our gravity model. So if you remember, I told you a gravity model is basically based on okay, so the idea is like okay, what is the zone population? So based on the zone population and its impedance between the zones, we try to create find the you can say just a moment, sorry. So we try to find basically, so again, just to repeat, so a gravity model is basically we understand that the zones that have more population attract each other, and they are and if they are further apart, so the distance between them is inversely proportional. So larger distance attract less, closer by attract more. And second is like population is more, you attract more trips. Population is less, you have lesser trips. Yeah. So this is the idea. And now, if you remember, we also had the the idea of different gravity models with their parameters, so using the impedance. Yeah. So sorry, the impedance function, not the gravity models. Let's go back to the slide so I have a better understanding. So we had a gravity model, and then we wanted, so the gravity model requires impedance, so it has the population and the distance is the impedance, yeah, and this impedance is represented not just by the distance but as a function. So we have to basically calibrate these impedance functions for the gravity model, and to do this we need to go back to wisdom and create a new procedure sequence that will be to calibrate these parameters and then use them in the trip distribution procedure sequence. So let's see the slides next. So next, first what we will do, so to do this we will first create a new procedure sequence, that is estimate gravitational parameters, and in here we will need to define the utility definition. So here the idea is like we need to create a new definition, right now. This is where you define the impedance function itself, right? So right now for simplification we are just using distance as impedance. So what we'll do, we'll click create and we will just choose the matrix, distance matrix, as the impedance function. So the values that is in the distance matrix is directly the impedance. That's it. Yeah. So we define the utility definition is equal to distance. So we don't have cost, we don't have travel time. That will have also the parameters or weights that define the utility. Yeah. So we just say the matrix one, and then next we go to the distribution, and inside the distribution we need to put the distribution or the TLFD table. So you have to create all the intervals. I'll show you how, and then simply what we need to do is like you need to create all the records by clicking this create button each time, and then you need to fill okay from to what is the from value and what is the to value and what are the total number of trips. The shares will be calculated automatically. Sorry, we need to write the share and the total number of trips will be created automatically. Yeah. So once you represent the distribution here, the next thing will be to choose the function type. Now function types are of two. So one is like either you have three parameters a, b, c, or you have just two parameters a and c. Now these are the functions that I was talking about just 2 minutes before, like which type of function you want to use for the gravity model. And right now let's say we choose the three parameters based functions, this one, and then we also choose doubly constrained, so balancing by multiple procedures. And we will execute this. So once we execute this, we should so let me see if we yeah, so once we execute this, the result will be basically the values, the calibrated values of a, b, c, the gravity model parameters. Yeah. And next what we'll do is like we will go to list to check to, if you want to see the parameters, you can go list od demand strata, and here you can add by saying here the select attribute, you can add the estimated gravity parameters and press OK, and you will see the estimated values of these three gravity parameters. Yeah. So I think you understand the idea how we can do this. So after this we have to do the trip distribution algorithm. So in trip distribution, this is the major part you have to do. So basically you have to create a TLFD to basically calibrate the gravity model, and this TLFD is created from the trip. So what we just did, we created a distribution, the trip length, observed trip length distribution, and now what we are doing is that we are trying to calibrate the gravity model. Yeah. So let's go back to Vism. So this is where we have left our Vism file. So this is the last point where we exported the distance matrix between the zones. And now the next thing that we need to go is to go back to like the calculate procedure sequence. It's already opened. And then just to create a new procedure sequence that is for, so I have to check. So it's probably demand again. Yeah. So inside the demand model, this procedure, that is to estimate gravitational parameters, gravitation parameters. Yeah. You select OK, and then in the reference object you need to define which demand group you want to do, and next you need to also define the utility functions, the distribution, everything that I just showed you on the slides. To start with, we'll create a new utility definition, and here you see the matrix value is 1. Instead, we will try to specify a matrix. So zone to zone, you will have different impedances. And this is okay. We select the matrix directly, that is this matrix, and we press OK. So we select this, and then press OK. And now we have specified in the utility our matrix. Yeah, and again, so if you want to create a new thing, so here we can have select matrix by properties and stuff, so we can have more different types of impedances. Yeah, so let's delete this one. So right now we have specified distance as the impedance. Now we want to do the distribution, and we want to choose okay. So this distribution is basically what we just had as the TLFD table. And to do this, we'll basically press create a few times. So once we press this and we say 1.2, and so what I'll do like 1.2, and then I'll say 2.4, and then I'll create again. So it will start from 2.4, and then I say 3.6, and then I create. So this is so 4.8, 6, and eventually 7.2. Yeah. So we basically have, so this is something that we don't need, so we remove this, and this is the distribution that we should have. And now we need to copy the shares that we had from the R file. Yeah, so if we go back and in the DLF table and we try to copy the shares, so I'm just gonna quickly go and copy the shares right now. So I've just copied the real FD table that we had. So this is basically defining the intervals from and to, and also the share this interval has. Yeah, the trips that are within this interval of the distance. Yeah. So now we also see the total number of trips here as well. Now the next thing that we need to define is the trip type, the function type. And here we'll basically select either this or this. So this is the idea. Okay, there are different types of gravitation model functions, and we have to choose one of them, right? So right now we are selecting the one which has three parameters, and we also select the doubly constraint. We can select different options. Okay, we can how many basically, because it's basically iterative based calibration approach. And what we are trying to do is like we're trying to tweak the values of a and c, and try a b c and find okay the function again which satisfies this distribution, right? So that is the idea. So this is the idea behind this procedure. Once we so that we can define a maximum number of iteration. Quality factor is basically okay how much convergence we get. So if we do more number of iterations, it will take longer time, but it will also help us find better values of ABC. Yeah. So once we do this, we'll go and okay, we don't need to save any outputs, and we'll press OK. And now we can just simply execute this. Okay, so okay, so let me just see this. So probably I have the error between for when I'm defining the distribution. So let me just try and create this distribution here. Okay, so I shouldn't have. Just let me just rewrite this again. So the error was basically we also had to define a pre-interval and the post-interval, which has like from nothing to 0, and from 7.2 to nothing, which has 0 say. So once I redefine the distribution as this, and I have the function selected with three parameters and the doubly constraint, we press OK, and then we can simply execute. We select this and we can execute, and this will basically execute the calibration of gravitation parameters. And to visualize these, we can go list, and we can go basically the OD demands and OD demand strata. So OD demand strata is basically where we have all the demand groups. And here because we only have one home-based work all demand group, we can add the selected attributes here, and we can say, okay, let's say gravitation parameters, right? So these are the three gravitation parameters, and we press here. Okay. Now this is how you can add the three gravitational parameters in the demand strata table. Now this demand strata table again will have all the demand groups that you are modeling. Right now we had only home-based work all, so this is the only record that we can see, and these are the parameters that we just estimated based on the TLFD that we created from the trip. Right. Yeah, let's just check the values if the values are similar as we have here. So yeah, they look similar, so everything is fine. Yeah. Almost similar again, I would say, yeah, but okay. So this is basically how you can calibrate the gravitational model parameters. So I'll just go back to show you once more. Um, where these values were. So we had the gravity model, the definition of gravity model. Then we had the impedance function. So how we create the impedance function. Right now we are just using distance as the impedance. So u is just equal to the distance, the utility. And the next thing is creating. So which impedance function is used to have the impedance for the gravity model, yeah. And this function is that there are a number of functions, and we are basically trying to calibrate the parameter. So the only difference between these different types of function is, okay, what are the different types of parameters that we are using? Either is just C, or is it C or B, or is it A, B, C? Yeah. So we are trying to right now use the combined version, that is like A U to power B and E to power C into U. Yeah. So we are basically we just basically estimated the A, B, C values based on the DLFD table. Now, what we'll do, we'll go to the next step of trip generation, because we already have a gravity model based on our observed trips. Now, what we will do, we will go to trip distribution algorithm, and in this, we will basically create a trip distribution procedure sequence, giving the gravity model that we just estimated and the production and attractions that we have from the trip generation. So let's go get in and try to see how it is done. So basically, to start with, we will basically create a new procedure sequence. Click on, so go to the procedure sequence space, and then click create, and then we will create, we'll select trip distribution as the new procedure sequence. Then inside the record for procedure sequence, we will select inside the reference object, we will select home based work all, and in the variant file here we will basically define all the different options that we have, like all the that we can specify in the tip distribution procedure. So first of all, what we need to find is the utility function. Now this utility function is basically the impedance that we are talking about, right? So before we already choose one impedance. If you see, so if you see here, to estimate gravitation parameter, we also had a utility definition. Here we chose distance because our distribution was a TLFD based on the car distance. Yeah? So that's why we chose a matrix. So this TLFD is based on a matrix that which we basically specified here. And next, now in the trip distribution, the impedance, the utility function will basically be the impedance we want to have. And here we are also using a simplified version, that is just distance. So this means that, okay, distance multiplied by 1. If you have travel times, if you have other impedance functions, you can also add basically the same utility function that we have there. And now once we specify the utility function, what we'll do, we will go to the, because once you will do that, what we will see that, okay, so just to show you again, so once we define the utility function and we press OK, we will already have the the function time as combined that I showed you before in our slides as well. And then we'll have these three values that we just calibrated and estimated, A, B, C. They will also show by themselves. And then the next thing that we want to specify is, okay, the constraints of trip distribution. Now this trip distribution is basically what we try to do, is we try to alternatively find the values from zone to zone. So the values in the odimetric cells, that is, so if we have 24 zones, we have 24 rows and 24 columns, and from zone to, so from one zone to all other zones, how many trips are going, right? And this is also extracted based on iterations. And to do these iterations, we have to specify some constraints, that, okay, you want to fix productions and you want to fix attractions. Yeah. So to define the constraints, we press on these on this button, and then here the district, that you'll see the direction. So we already have the function time fixed as combined, because we estimated three parameters, A, B, C. The next thing what we are doing is, like, we need to define the direction of distribution constraint, so which we say that, okay, constraint production. Now this means, as if you remember, we already had the discussion that in the trip generation, that For home-based trips, we are more reliable on the predictions because predictions are based on population and we are certain that population data is more correct, right? If we have a demand group that is non-home based, we might want to constrain the constraint attractions. And the reason was that, okay, when you do non-home based trips, attractions are more reliable because the production of these non-home based are also based on population, which is home, right? And in this population, production is not directly representing anything in non-home based trips, so that's why attractions are more reliable. So if you have a demand stratum that is non-home based trips, for non-home based trips, I would probably suggest to use constraint attractions. Yeah. And then next is also, like, once you do this, next is also to balance the matrix. You can choose, okay, for doubly constraint, so for matrix balancing, initial matrix balancing, how do you want to start? So even you want to do doubly constraints, you want to first fix the production total, and then you want to, so in iteratively you want to fix one of them. So which you want to start with? You want to always start with the production total for home based trips. And so once you are able to choose both of them and you press OK, you just need to run the procedure sequence to run the step of trip distribution and get OD matrix as an output. So once you run this, you can go back to matrices and check that there's also a demand matrix, where inside this demand matrix you have a distribution matrix that is for home-based work all, and it has basically an OD matrix for all the zones as rows and columns, and these are the values that are within the zone. Yeah. Now, one important thing also is that, okay, there shouldn't be, actually we should set the internal internal trips as 0, which we are not doing it here. But the basic idea of an OD matrix is that we are not basically so using an approach of this four-step modeling, having zones and having OD matrices, that we cannot actually represent the trips that are within one zone, because we are not certain how many people are going out within one zone for walking, biking. And what we try to is, like, we try to create an optimized size of all the zones, so that we minimize the trips that are within one zone. Yeah. And this is done, we already had a discussion this before as well. Yeah. So this can be done basically, either we have homogeneous land use within zone, and also we also try to reduce the sizes of it. Yeah. Of the zones. So that's it. So once we have the OD matrix, we can also see it as an attribute of OD pair table, and this is what we are doing here. So we go to OD pairs list and OD pairs, and here we have the matrix value 2 as the OD pair trips. Yeah. And now what you want to do, if you remember, like I told you in the start, that once you have the results of the trip distribution, what we wanted to do was we wanted to compare how well were we able to calibrate the gravity model. And to do this, we basically will try to extract the same OD pair table again, with the modeled trips with the OD matrix, in an Excel file, so like this. And then we will go to R again and we will try to find the modeled TLFT. Yeah. So but before that, let me just perform the steps of trip distribution again. So we will go back to our Visum file. Let me just check this. And here we will basically go to again to procedure sequence. We already estimated the estimate gravitation parameters. So next, what we want to do is, like, we want to create a trip distribution procedure, and we'll go to create and then demand model trip distribution. And inside here, we want to choose a reference object again, which will be our demand group, which we are trying to create the trip distribution step. Yeah. And then in the variant file, we'll basically choose all the options that we need to specify in this step. Here, we will basically first of all define the utility function. And as I told you, right now we are just using the utility function basic as the distance between the zones. Yeah. Next, we need to define the function type, that is okay combined. And here okay, just let me see again. So we want to use the function type combine, but we will not need to specify this if we want, if we set this box as ticked. So that says that apply estimated parameters. So we estimated some parameters just before this step, which were the values of a, b, c, and if we check this box, we actually implement those values here. So these are the values, and to use these values we can have only one function, that is called combine. So that's why we don't even need, we cannot change the function. If we use another type, just trying to extract b and c, just two types, we can do that as well in the estimate gravitational parameter procedure. Then we might have options in choosing which function type we want to do. Yeah, so once we do this matrix and we do the apply estimation parameters option selected, and next thing that we can do is like we can define the constraints as we were discussing, and to do that we press this button and then we come here and we specify constraint production for the direction of distribution, that the productions will stay more same as they were in the start of estimation, while the attractions will be rearranged based on the prediction. The second thing is also for doubly constrained balancing, if you want to do it or not. But if you want to do a double constraint, that okay, we do the production first in the first iteration, then we do the extraction, and we change the production in the next iteration, and then so this is the second method that we can do, which will do doubly constraints. So each time it will constrain one of them and it will do the iteration to find the values inside the cells of the Nodi matrix that satisfy both the production and the attractions. Yeah, so this doubly constraint we'll select, and this and here we'll select the production total and press OK. And once you will implement these constraints, you just need to run the procedure sequence, selecting this as active and pressing this play button, and this will basically run the trip distribution function. And to visualize our OD matrix, we need to go to matrices, demand matrices. Inside demand matrices, we will the OD matrix can be seen under matrices, demand matrix, zone, data matrix, and distribution, home-based work cost. If you double click this, you can see the OD matrix that was the output uh, from our trip distribution step. And the next, what we wanted to do, like this is the output for trip distribution. Now we also want, so this is based on a gravity model that we calibrated from the observed TLFT of our trip data. And now next we want to do is like what is the actual accuracy of our calibrations, and to match, to check that accuracy, what we want to do is like you want to create a modeled TLFD from this OD matrix and want to compare the modeled versus observed TLFT. And to do this, let's go back first to the slides and go through the next slides of how we can create the model TLFD and how we can find the coincidence ratio and check how well are we able to represent the observed TLFD on our model. And so to do this, so the next step would be so first what we want to do is like we want to export the OD matrix in form of the OD pair table, which it will add another column that has all the OD pair and its strips, and then we'll extract it as an Excel file. So we'll first extract it as a database, and then we'll create a new Excel file and we'll load that database and save the Excel file. Yeah, I'll show you this in the next steps on hands-on. uh, Now to evaluate the trip distribution results, first we'll do the same step as we did for the observed TLFD. We will load the model trips, and then we will basically create a TLFD table. So now the input would be the model trips, and we will mutate the distance. We'll create a new we'll mutate a new upper limit column which has these 6 same different rows of the upper limit of all the intervals, and then we'll group by these intervals using this constraint, distance is less than the upper limit, and then we'll summarize the the trips, the home-based work trips that we have, the model trips that we have for all the intervals. And this we'll save in total model trips, and then we'll also mutate another another column that will be like modeled share. That will be the total model trips for each row divided by the sum of the whole column of total model trips. Yeah, and this will rather this will basically give, if you can see the visualizations here. So first what we'll do is like we will load the OD pair table that we'll extract from the model, and it will look like this. This is from zone to zone, the distance between the zone pair and the number of trips. Next, what we'll do is like we have the upper limit, we have the total model trips, and we have the model here. This is the output from the piping code given here. And now because we have the TLFD modeled and TLFD observed, we can basically find the constants ratio as well. So this is the histogram that we have from the modeled TLFD, and to plot this, it's similar as the observed TLFD. We want to use the ggplot, and inside the ggplot we will create a histogram, the geometric histogram with these breaks as the which were the same as the upper limits, and we'll plot the TLFD. Now, this confidence ratio, what is the confidence ratio? So first, let's go a bit of its description. So basically, confidence ratio is an indicator to compare the observed versus modeled TLF distribution. So TLFDs, so trip length frequency distributions. Yeah, and these are given as by this formula where the numerator is the minimum of both the modeled and the observed TLFD shares divided by the maximum of either the observed or the modeled TLFD. Yeah? So we are basically taking a ratio of the minimum share for the given interval divided the maximum share of the given interval. And to implement this formula, what we'll do, we'll try to manipulate a bit our TLFD tables for both observed and modeled. And this can be done basically. First, what we'll do, we'll merge both the observed and modeled TLFD tables, and we'll have a merged TLFDs with a full join of TLFD table and model TLFD table. Then the next we'll create a new column by using the piping mutate function. So basically you have merge TLFD is equal to merge TLFD. So we are not creating a new table, but we are just mm, overwriting this merge TLFD by mutating, which is like adding a new column named minimum share and maximum. So we are adding two columns, and the minimum share will be added based on this thing. So the minimum of share and model share. So this will be a column that will be the minimum of the two, share and model share, and the other column will have the maximum of both. Yeah. And once we have these new two columns of the minimum and maximum values, what we'll do, we'll calculate the confidence ratio as the sum of the minimum share column divided by sum of the maximum share column. Yeah. So so this is the visualizations in R. So first we have the merged DLFT table, which has both the observed trips share and the model trips and its share. Next, we'll also see the confidence ratio. So next we'll create a minimum share and maximum share columns. So this is, as you can see, is like minimum of these two columns. This will be the minimum of these two columns, and this will be the maximum of these two columns. And then once we have this, we'll basically create a ratio of sum of this and the minimum share column and the maximum share column, which comes out to be 0.938. So which means 93%. So the value that is closer to 1 will be more accurate or more better in terms of results. So we are able to represent our TLFD from the observed trips to the model trips. Yeah, so let's go back to the R file again. So first what we need to do is so let's go back to our Visum model file. So first what we need to do is like we need to export this OD matrix into an Excel file, and to do that we need to go to network, OD pairs list, OD pairs. Here we need to add the attribute that is a matrix. So what is the matrix name? It's distribution. Yeah, distribution. So you see, if you're at distribution, you get in the matrix value, this is the distribution, and we'll add this as the column and we'll press OK. So this is the new column that we want to add. And next what we'll do, we'll want to export this as a database. We'll do the same things that we have done before. So we'll export this as an access file, and these are the model trips. Yeah, so I already have it. I'm just going to overwrite it because I had it in the when I was building the lecture. So and then we press OK. So now we have the database, and now we'll create a new Excel file. And creating a new basic Excel file, we will load a new data. So we load data from database access, and then we will simply load the access file that we had. So let me just go back quickly to the lecture. So yeah, we will select the file that we just saved, the mdb format file. And yeah, here we can see, okay, we have the OD pair table that we want to extract, and this is the value, and then we'll simply load this. Yeah. So once our access database is loaded, we want to save this file named as the modeled trip file. So we will give the path in the R script to load this file. One important thing again is to change the values for this for its columns. This can be done again in Visum, but I'm still doing it here manually. So this is distance, and this is home-based work trips. So this is what I have specified in my R file. So let me just quickly go and check. So I am specifying the await home-based work trips. So this is what I also specify here, and then I simply save this file, calling it as model trips dot excel file, so excel file format, and I'll close this. I'm gonna put this in the same directory so that I can load this into my R file, into my R code. So let's go back to the R code, and basically we were finished till here. So what we did, like, we had the TLFD and we plotted this TLFD. Yeah, so this was our TLFD for the observed, and then we created a TLFD table that we could have seen here. So this is the TLFD table that we also used for the gravity parameters calibration. Now next we are trying to do is basically we are trying to load the model trips, and to do this we again gonna use read excel function, and this will basically load the excel file as the modeled trips as well. So this is here, and this is the file that we just saved, which has the from zone to zone, the OD pair, and its distance, and the number of home based work trips. Next, we can also create a plot of this TLFD. So now this is the modeled TLFD plot, similar histogram plot that we created for observed. And to create a model TLFD table, we will use the same code as we used for the observed one, like this, which has the upper limit column with the constraints. Then we group by the all the interval trips by the constraints, and then we take the sum of home based work trips. So this is the value, this is the column name right here. So we sum the home based work trips for all the groups separately, and then finally we mutate to have a modeled share. So we create another column which will have the modeled share instead of the of like which is like the ratio between total model trips of each row divided by the sum of the total model trips column. Yeah, so to do this, once you can simply run this, and what you'll see like is model TLFD table looks like this. Yeah, so the upper limit, total model trips in all the intervals, and what is the model share for these total model trips. Yeah, now once we have the modeled TLFD table, and we also have the observed TLFD table, that is this, what we'll do, we will try to find the constants ratio that we just saw in the slides. And to do that, first we will merge the both TLFD tables, and to merge them we use the full join function, and we have the TLFD table and the model TLFD table, and we merge them by the upper limit as the index for mergence. Yeah, so once we merge this, we have the merged TLFD table which has the upper limit and both observed and modeled trips and their shares. Next, what we want to do, we want to create two new columns for minimum and maximum of the shares, and for that we use the piping with mutate function. Yeah, so we use this code basically to add two new columns by the function of mutate in this merge TLFD. In these columns are minimum share and maximum share. The minimum share is the minimum of both the model share and the share or the observed share that is basically the observed share, right? So the minimum of these two columns is in this column, and the maximum of these two columns in this column. Yeah. And now what we'll do to find the coincidence ratio, we need to divide the sum of the minimum share column divided by the sum of the maximum share column. And to do that, we'll basically do this simple step of dividing this and finding the coincidence ratio. And here you can find the coincidence ratio in this variables workspace, that is 0.94 or 939. Yeah, we can also plot, you can also extract the answer here as well. If you have a lot of variables, this is the value of the coincidence ratio. Yeah. So I think you're able to follow up and understand how we can find the coincidence ratio in R. It's rather very simple. So again, the coincidence ratio was basically the minimum of the share for modeled and observed divided by the maximum of the share of modeled and observed. And if you see, the summation is outside the minimum. So first we created columns for minimum of both and maximum of both, and then we basically take the sum of minimum column and maximum column, and then for the sums we take the ratio and we find the cost ratio. Now, so that's it. So that's basically the idea now. So of trip distribution, where we basically started from the production attractions that were the output of the trip generation, and then to convert this production attraction into an OD matrix, we needed to do the step of trip distribution, and this conversion require a gravity model that defines, okay, which zones will more likely to go to which zones, right? So which the productions from which zones would likely to go to the directions of which zones. Yeah. So this is done by estimating a gravity model. So we estimate the gravity model parameters by the observed TLFD, which we extracted from the trip survey. And once we have the observed TLFD, we calibrate the gravitation model parameters, and then we used these parameters to do the procedures, the sequence of trip distribution. And once we got the answer or the results for the trip distribution, which was an OD matrix already, what we tried to do was we then compared the modeled TLFD or the TLFD that we had from the OD matrix that was the output of the trip distribution, and we tried to compare the both TLFDs to check how well we were able to calibrate also the gravitation parameters, so that we also know that how well we are actually able to replicate the observed TLFD, or what we observed the behavior of people moving versus in the model. Yeah. And also I had some new tasks. So probably so next week what we're planning is also to have a live session. And what I want you to do is I want you to do a homework for for us for basically. So what we want to do is, like, right now we finished in this lecture, what we did was, like, we finished a home-based work based trip distribution. So we had only one demand group, and this one demand group we did trip generation, we had production attractions, and then we estimated the gravity model, we did the trip distribution, and now we have an OD matrix for home-based work all. Yeah. So now what I want you to do on in your homework is basically, I want you to try and do a homework with this demand model, which has trip purpose based classification in home based work, home based other, and non home based. And next, I also want you to work with person groups with car. Now, the person groups with car only means that you will work only with the trips that are done by car. Yeah. So first you will need to create inside the activity pair in your demand model three different activities: home-based work, home-based and non-home-based. And in the person group you will have only one person group, that is with car. But when you're gonna do the processing in R, you will have an extra constraint that will say that I want only the trips which are done by car. Yeah. And next week what we'll do is, like, you have this 1 week to do the homework and to try to fill out the same exact process. So you will have to do the trip generation with these three different demand groups: home-based work car, home-based other car, non-home-based car. So you will have production attractions for these three demand groups, and then you will also do the trip distribution for these three. Yeah, and next week we'll have a live session where first I will try to give you, so first 15 20 minutes I will spend some time probably to give you the answers if you have any questions for the homework, and then in the last in like 1 hour I will try to show in front of you the solution of this homework, so that you are well understood how we can do these two steps of generation and production with different demand groups. Yeah, and this will be a nice revision session for these two lectures of trip generation and distribution. And that's it from my side from today. We have finished basically the lecture for trip distribution, and next what we want to do is to first do a revision next week, where you will have the homework, a live session, and interaction with you for this, what we have done so far for trip generation and production, and how well you have been able to understand, and how what if you had any problems with the homework. And next, after that, we will have another session where we will talk about the moisture. So if we go back, let's try and go back to the schedule here. So next week we're gonna have mode choice lecture. We will try to use the tree choice based methods to to create home based work mode share. So people who are coming from home to work, what are the different modes they choose? So we'll have the trip. We already have a trip survey, so we will try to create OD matrices. So right now we have just one OD matrix, that is home based work all. Now we'll have OD matrices for home based work all by car, home based work all by public transport, and home based work all by bike, right? So the three modes that we have. So the third, so this now I will rearrange the schedule. So next week on 17th we will have a live session, and then on 24th we will do the mode choice. There's a fourth step more approach, so I will rearrange the schedule, and I'll update it in the next lecture for sure. Yeah, and so that's the basic idea for now. So I give you best of luck to do your homework, and if you have any questions, of course you can send us by email all your queries. Anyway, we will have a live session next week, and we can discuss one on one any of the problems and queries you had so far for these 2 or 3 lectures. Yeah, so see you again next week. Have a good day and a good week. See you then. Bye.